Our new unit this term is counting methods or combinatorics. So let's get stuck into it. It's pretty different and yeah, it's lots of fun. If there are 25 students in 7D, how many different ways are there of choosing 5? How do you begin to even answer that? Like, would you sort of go, all right, let's just imagine each of the students, all right, and if I took, say, Mary and Jane and blah, 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 you know, it would take you forever to sort of think about how many different configurations there were of this particular 5 that you were trying to choose. How many different ways could you order all the different cards in a pack of 52, or how many different shuffles are there? It's evident that we need to develop some methods to be able to count in these situations, because counting up the number of ways this is possible allows us to actually work out some probabilities and things like that. Right, so first of all, we'll focus on what we call the addition and multiplication principles. All right, so the addition rule, nothing to do with the addition rule from probability. Okay, completely different. To choose between alternatives, simply add up the number of choices available for each alternative. So if one action has X options and the other mutually exclusive action has Y options, then there'll be a total of X plus Y options. This or this can happen. Okay, so Ms. Kerrigan is going to a party. She can't decide whether to wear a dress or jeans. She has 4 dresses and 3 pairs of jeans. How many options does she have? Well, what we're presuming is, so we've got jeans, which is the 3, and dresses, which is 4, and she's either going to wear a jeans or a dress, so that's 4 plus 3, that's 7 possibilities. Okay, notice that I added them, I used the addition rule. Sam goes to her wardrobe to select a pair of pants to wear today. She has 8 pairs of trackies, loves the trackies, 3 pairs of leggings, 4 pairs of jeans. In how many different ways can she dress herself? Well, assuming she's wearing a top, because that would be appropriate, then we're going to say that there was tracksuit pants, there was leggings, and there was jeans, and she had 8 trackies, 3 leggings, and 4 jeans. So we're just going to add those together, which is 11 plus 4, which is equal to 15. So there's 15 different ways of dressing herself. Tony needs help with a particular maths question. She has 5 friends that she could ask for help. So friends is 5. She could help her teacher, 1 I presume, her tutor, also 1 I presume, her brother, 1, either of her parents, 2. In how many ways can she obtain help for the question? Well, these are all of them. So it's either 1 or the other, or the other, or the other. So 6, 7, 8, 10. 10 different ways. All right, now let's have a look at the multiplication rule. When sequential choices are involved, the total number of probabilities is found by multiplying the number of options at each successive stage. 2 stages with m and n options result in m times n choices altogether. When something and something occurs, what we do is we multiply. All right, so here we go. We've got Tom and Jerry have a car sales yard. They stock cars from 6 different manufacturers, A, B, C, D, E, and F, like Toyota, Ford, Alfa, Porsche, Ferrari, and Kia. Each manufacturer supplies the cars in 5 different colors. There's the colors, and all cars can be purchased as a manual or an auto. All right, so if you imagine this would be like thinking about a tree diagram, right, where we've got 2, 3, 4, 5, 6, 3, 4, 5, 6. So A, B, C, D, E, and F. And then there would be 5, is it 5 of them? And then each of them would be 2. And what you're looking for is the number of different ones that would come out of this. Now you can see that the tree diagram is really difficult to draw there. So it's much easier to think about it like this, the multiplication rule. How many choices are there going to be? There's going to be 6, lots of 5, lots of 2 each. So how many different types of car is available? It's going to be 6 times 5 times 2, which is equal to 6 2s are 12, 5 12s are 60. All right, now what we'll do is we'll limit the tree diagram a little bit. We'll take out some of the options. So if a person requires a red car, so it's still these 6 manufacturers, okay? So it's these 6 manufacturers here, but the only color they produce is red, or the only one that's acceptable is red. So that's actually going to be 1 at each of those stages. It's going to be just 1 of those branches, not 5 of them. And off those branches, what we're going to get is the 2 types of transmission, which is auto or manual. Okay, so what we've done is just looked at each of those. So here we've got manufacturer, color, and trans. Here we've got manufacturer. Notice the difference in color there. We're now restricting the options from 5 down to 1, with that transmission still being either auto or manual. That's going to be 12. Right, this last one's particularly tricky. If a person wants to purchase a car from a particular manufacturer, color, and automatic transmission in mind, how many different types of cars could they purchase if at least 2 of the criteria were met? Right, well, let's think of a car that someone might want to buy. So they might want to get an A car, so a car from manufacturer A. They might want that car to be red, and they want that car to have an automatic transmission. Now let's think about the number of cars that will meet these requirements or be acceptable, because remember, this person wants at least 2 of their criteria to be met. So we've got car A, or manufacturer A. It's a red car and it's an auto. Now, at least 2 of the criteria will also include manufacturer A in red, but a manual. That will actually meet this person's requirements of at least 2 of the criteria. Now, what else will meet their requirements? Well, they could go to Carman and get a car manufacturer B, get it in red, and it could be an auto. Now, what satisfied their requirements? It's a red car and it's auto. They could go to C, grab a red car, and it could be an auto. D, red and auto. E, red and auto. And F, red and auto. All right, now the last one that we'll consider is that the color doesn't matter. All right, so we'll say that car manufacturer A and an auto, and we're going to say that that would be the other colors. I forgot what the other colors are. Blue. Okay, so we could have A, blue, and auto. Now again, that meets 2 of the requirements. We could have a, sorry, I forgot the colors of the cars here. White, black, silver. A white and auto, a black and auto, and a silver and auto. Right, and they will also meet the requirements. So there is all of our cars that will meet the requirements of at least 2 of the criteria. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We've got 11 in total. Now, I remember a couple of years ago, I taught the problem by just simply going, all right, at least 2 of the criteria means if we've got a manufacturer, a color, and a transmission, then there's 6 different manufacturers. And what we'll do is we'll say that there's one particular color that we're focusing on and 1 type of transmission. That was 6 cars. Then we considered the other option, which is 1 manufacturer, 5 different colors, 1 different transmission, which is 5. Now what happens here is that we would actually stop and add those together to get 11 as well. Now, it looks really simple, but what the problem is that students always then go ahead and match or write the other criteria, which will be 1 times 1 times 1 equals 1. That's all 3. And 1 times 2, which is 2. And the answer invariably to this question students will get is 14. The problem is that the students tend to double count on this, okay? That what they don't understand is that one here has already been counted in that, and those two have already been counted up here as well. So I've gone to this method to explain the problem, which is to actually just brute force it out a little bit, because students have a little bit of difficulty just seeing when they've double counted. All right, no doubt, tough problem, that one. Let's see if it gets any easier. A student at Being a Good Secondary College is required to select 3 elective subjects. The electives are arranged in 3 groups, and a student must select 1 subject from each group. In Group A, there are 8 possible subjects. Group B, 7. Group C, 6 possible subjects. No subject is repeated in any group. What is the total number of elective subjects offered? Or offered, I think I said offered. So we've got Group A, Group B, and Group C. We've got 7 in Group B, 8 in Group A, and 6 there. There's a total of 21 subjects. How many different choices of the 3 elective subjects can be made? Now remember, what's going to happen is they select A, which is 1, 2, 3, 4, 5, 6, 7, 8, followed by 7, followed by 6. The tree diagram is going to be chaos, but hopefully you understand that this is the multiplication rule. So 7 8s are 56 times 6, 6 3, 6 5s are 33, 336. If a student has a particular preference for a subject in Group A, so here's A, B, and C. So Group A is like, yeah, decided, like I'm doing maths methods, that's non-negotiable. Will not remotely consider 2 subjects in Group B. So there's 7, so that means we're down to 5 electives. Nothing mentioned about C, so we assume that, all of them are all right. Then we've got a total of 30 possible options. Sammy loves ice cream and loves Delopolot Ice Creamery. They have 12 flavors of ice cream. Let's say the ice cream is 12. 2 types of cones, so cones is 2. Choc, straw, caramel, vanilla sauces, so that's 1, 2, 3, 4. So sauces is 4. Toppings of crushed nuts, flake bits are M&M, so the toppings there's 3. If Sammy orders a cone with 1 flavor of ice cream, 1 topping, and 1 sauce, how many different orders are possible? Well, a plethora, I would say. We've got ice cream, we've got topping, we've got sauce and cone. So we've got ice cream, which is 12, toppings, which is 3, sauces, 4, and cones is 2. And we're going to multiply those out because it'd be like a tree diagram. 3, 4, 5, 6, 7, 8. It'd just be crazy though. 3, etc., etc. It's just going to be too difficult to draw that via the tree. So 3 12s are 36. 4 times, let's double 36, which is 72. 4 lots of 72. 8. 2 4s are 8. 7 4s, 32. 328. I'll get that in my notes. No, what have I done wrong there? Let's try that again. 12 times 3 is 36. 72. Yeah, what's wrong with that? 7 4s are 28. 288. I'm not sure what I did wrong the first time there, but All right, if Sammy does not like flake bits and always wants caramel sauce, how many different orders are possible? So does not like flake bits. So we've got ITSC. So does not like flake bits. So that means that one of the toppings is no-go. So toppings is now down to 2 toppings. Wants caramel sauce. So the sauce, there's only one acceptable option. How many different orders? So there's still the 12 there, and there's 2 types of cones. So that's going to be 12 twos are 24. 24 times 2 is 48. Right, so there is some great ways to count number of different configurations that are possible, rather than just sort of rearranging and hoping you've counted them all. This is more systematic. All right, let's get on to arrangements. So for this exercise or topic, you'll need to be comfortable with factorials. All right, so evaluate the following, where n factorial is just n times n take 1 times n take 2, all the way down to 1. So 5 factorial is not actually just 5. What it means, actually, that was me trying to be emphatic about the 5, but that's not what that means. What that means is that's 5 times 4 times 3 times 2, and it would be times 1, but we know that anything multiplied by 1 is just that thing, so I'm not going to multiply by 1. Now we can evaluate this. It looks pretty nasty, but it's actually quite easy. 5 fours are 20, 3 times 20 is 60, 60 times 2 is 120. All right, what about 6 factorial? Well, that's going to be 6 times 5 factorial. And we already know what 5 factorial is, that's 120. So that's going to be 6 times 120. 600, 6 twos are 12, 720. All right, 1 factorial. Okay, that's just going to be 1. Right, here's an interesting one. This is 0 factorial. Now, 0 factorial is 1. Right, now, I remember back in the day, I was just told that that's just a fact. Okay, but if you want a little bit more information on that, I implore you to follow this YouTube link here to work out why 0 factorial is actually 1. There's a great explanation of that. It gets pretty heavy after about 4.5 minutes, but before that, very accessible. So I implore you to go and watch that. It's got the Professor James Grime in it, and he's very entertaining. All right, 8 factorial over 7 factorial. Ooh, looks tough. Well, that's 8 times 7 times 6 times 5 times 4 times 3, etc., etc. But wouldn't it just be 8 times 7 factorial over 7 factorial? Yes, it would. And notice that 7 factorial over 7 factorial will just cancel out. That's actually just a really complicated way of writing the number 8. Right, this one here is going to be 10 times 9 times 8 times 7, or 10 times 9 times 8 factorial over 8 factorial. The 8 factorial cancels out, leaving us with 90. Easy. Oh, this looks so difficult, so difficult. Not really. 100 times 99 times 98 times 97 times 96. But forget that. I'm not going to do any of that because the 98 factorials cancel out. This is just 99 times 100, which is 9,900. Right, this one here is going to be 20 times 19 times 18 times 17 factorial over 17 factorial times 3 times 2. So I'm working on this one here, times 1, but I'm not going to write it in. Okay, the 17 factorial cancels out. But here's the beauty of this. I'm going to cancel 2 with this 18, leaving 9. Cancel that with that to make 3. And what I'm left with is 20 times 19 times 3. All right, let's do that one. So 3 times 19 is going to be 20, 40, 60, 57. So that's going to be 57 times 20, which is going to be 57 times 2 times 10, which is going to be 114, 140. Hopefully I got that one right. Let's check it actually. So this would be a good time to jump on your calculator and go to main. Let's get rid of all of this. And what we're going to do is open up the soft keyboard. And you know you're getting into some serious mathematics when you have to go down into advance. All right, this is the hardcore section of the calculator here. Now what we're doing here is there's the factorial button, that one there. So what we're going to do is say we've got 20 factorial over 17 factorial times 3 factorial. Hey, I got it right. Good job. Okay. So yeah, watch that video. Really good video. All right, arrangements or permutations. So you might have heard the word permutations used in common language. Jackie, Lucy, Sarah, Alex, and Mary are athletes and the only competitors in a 100-meter race. In how many ways can the first 3 places be filled? Assume no ties. You could list them all. Right, and someone has gone and done that. I didn't do this. Some other teacher that I pinched these notes off has actually gone ahead and listed the number of ways in which the first 3 places could be filled. So it could be Jackie, Lucy, Sarah. Jackie, Sarah, Lucy. Sarah, Lucy, Jackie. My brain is already grinding thinking about this, okay? So what do we got? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6 times 10 is equal to 60. So list them all. You'll notice that a different order or arrangement gives a different winning result for the race. Okay, so notice that Jackie, Lucy, and Sarah is different from Jackie, Sarah, Lucy. Like at the end of the swimming carnival, if you finished the race and I gave each of you just like a red token and said you're either first, second, or third, you're either first, second, or third, you're either first, second, or third, it doesn't really matter. The winner of the race is obviously going to look at me and sort of go, hey, Mr. Miller, like I won though, like isn't there something better if I won? So notice that this is a different arrangement to this, which is a different arrangement to this, okay? And this is important when order matters, okay? In finishing a race, order matters. Right, is there a quicker way of getting to the answer? Well, yes, there is, okay? So you're not gonna have to do this stuff here. What we do is we think about this using what's called the box method. In the box here, what we do in this first box is put in the number of possible ways first could be filled. And that is 5 possible ways. It could be Jackie, Lucy, Sarah, Alex, or Mary. And we can also consider it like a tree diagram. Jackie, Lucy, Sarah, Alex, and Mary. Now from there, if Jackie wins the race, it can be either Lucy, Sarah, what's that other one? Alex, or Mary. And if Lucy comes second, then it's going to be only 3 competitors after that, Sarah, Alex, and Mary. And we can continue to do this, but if we understand that multiplication principle, it's going to be these 5 multiplied by these 4 multiplied by these 3. 5, 4, 3 with multiply signs here, which means that 5 4s are 20. 20 times 3 is equal to 60. Much easier way of thinking about this problem than a tree diagram or doing this. So the number of ways first can be filled is 5. The number of ways second could be filled is 4 because there's only 4 other competitors left. And then after we've got those 2 competitors filled there, there's only 3 of them remaining. A photo is to be taken of a group of Year 12 students. No, of 12 students. How many different ways are there of arranging the group? Well, I imagine it like this. We've got these 12 girls standing around here. There are 3, 4, 5, 6, etc., etc. I'm not going to do it all, but I imagine them all standing there going, you know, all right, oh, is he going to pick me? Is he going to pick me? How many different ways are there? Well, first of all, I've got 12 to choose from. Then I've got 11 to choose from. Then 10, then 9, 8, 7, 6, 5, 4, 3, 2, 1. Or we can note that that is actually just 12 factorial. All right, and so there's another video there that I think you should go watch. I think that's the one where Stephen Fry talks about 52 factorial. Check that one out, that's a good video. What about if the photographer only wanted a picture of 5 students from the 12? How many arrangements now? Now note that the wording in your notes might look a little bit different, and because I updated this, I thought the way it was written was a little confusing. So I wanted a picture of 5 students from the 12. Well, what we would do is there would still be the 12 girls up there. All right, so I'd be looking at all 12 and I'll go, wait, from these 12, I've got 12 possibilities, then 11, then 10, then 9, then 8. And the rest of the girls are unfortunately going to miss out. So this could be actually noted to be written as this, 12 times 11 times 10 times 9 times 8, okay, and left at that. Or we could do this really bizarre thing here, which is actually to write 12 times 11 times 10 times 9 times 8 times 7 factorial over 7 factorial. Now, why can we do that? Because they cancel out and just leave us with that. Now, why is this important? Well, there's a formula that this leads on to. So in general, the number of arrangements or permutations of n objects in groups of size r is given by this. This is the syntax. We write npr equals n factorial over n take r factorial. All right, so for the 5 student photographer question, 12p5 means the number of ways to arrange 5 students from a total of 12 students. All right, and we can use the formula on that. I'll just show you quickly. So 12p5, number of ways to arrange 5 students from a total of 12. So n is this thing here. That's going to be 12 factorial over n take r factorial. So that's n take r, that's 12 take 5, that's over 7 factorial, which is equal to 12 times 11 times 10 times 9 times 8 times 7 factorial over 7 factorial, which cancels out, which gives us that, which gives us that, or that. Notice that the box method is fantastic here. So you don't really need that formula if you understand how to use these boxes. All right, let's try it out. Jamie has 8 different books, but there is only room for 3 of these books on her bedside table bookshelf. In how many ways can Jamie randomly select the books and arrange them on her bookshelf? All right, so basically she looks up, okay, or she looks at the 8 books. There's only room for 3 of them. So we draw 3 boxes. And when she looks up, she's got 8 to choose from. Okay, so she chooses one of them, which means that she's got 7 left after that, which means she's got 6 after that. So that's going to be 8 times 7 times 6. 7 8s are 56. 56 times 6. 6, 3, 5, 6 is a 30. 3, 36. I can use the formula. So we're going to say that 8p, what was it? Select 3, 8p3 equals 8 factorial over 3 removed from 8 is 5 factorial, which is 8 times 7 times 6 times 5 factorial over 5 factorial. They cancel out. That's 336 when you multiply those out. How many 4-digit numbers can be formed from the digits 6, 7, 8, and 9 if each digit may be used once only? So that would be like, if you consider the tree diagram, 6, 7, 8, 9. If you chose the 6 first, it wouldn't be available. So it would be 7, 8, 9, etc., etc. from there. So you can see here it's going to be 4, followed by 3, 2, 1. Okay, so let's just draw out our boxes. So I've got the 4 digits all up for grabs first of all. Then there's going to be 3 digits left after I've made my first pick. 2 digits, 1 digit. So that's 4 times 3 times 2 times 1. That's 12, that's 24. What about if there's no restrictions? This is kind of like replacement. Okay, so if I chose 6 first, I could choose 6, 7, 8, and 9. So it's actually going to be, first choice is going to be 4 possibilities. Then I'm going to have 4, 4, and 4, which is 4 to the 4. What's 4 to the 3? 64 times 4, which is, it's 256. 4 4 is 16, 1, 6 4 is 24, 25, 256. All right, once only with the value of the number greater than 7,000. All right, so we've got a restriction here, and let's take care of the restriction first. And it's very important that you note that. We take care of all the restrictions, and then we see what's left over. All right, so if a number greater than 7,000 has to happen, then 7, 8, or 9 has to be chosen first. There's only 3 possibilities. It's like in a photograph or something like that, saying that the first student chosen must have black hair. And you look across and there's 6 blondes or 6 brunettes or whatever. You'd be like, okay, well, I've got a fairly small number of choices, or the number of choices I've got is reduced. So that first one there is going to be 3. Then I've chosen from that. I've made my pick, right? Which means how many are left over? Well, there's still 3 left over after that. And then there's going to be 2, and then there's going to be 1. So this is 3 times 3 times 2 times 1. 3 3s are 9, 9 2s are 18. All right. How many different arrangements of 9 people are possible if 3 people are chosen at a time? So that's going to be, so we're choosing 3, so that's 9, 8, and 7, which is 9 times 8 times 7. 9 8s are 72. 7 2s are 14, 1. 7 7s are 49, 50, 504, I think. Let's try that one out. Yep, all right. 5 people are chosen at a time. So we've got 9, 8, 7, 6, 5. All right, so it's going to be 504 multiplied by, so 9 times 8 times 7 I already know. 6 times 5 is 30. What's that going to be? 3 lots of 504 is 1,000, 1,500, 12. With a 0 on the end, I think. 504 times 30. 15128. Yeah, cool. All right, just do the multiplication over here. So do 504 multiplied by 3, which will give you 1512, and then you have to multiply by 10, which will mean that you add another 0 on the end. 4 people are chosen at a time, but one particular person must be chosen first. All right, so here's our 4 boxes. So I've got to make my first choice, but like for whatever reason, someone's pulled rank and gone, that person must be chosen first, a bit of favoritism, all right? That means that option 1 is there's only one option, all right? Now, there was 9 people there. How many are going to be left after that? It's going to be 8, 7, 6. So this is actually 8 times 7 times 6. 7 8s are 56. I think I did this one before. I think it's 336. 6, 3, 336. You'll notice some of these numbers come up. So the more you get into this unit, you'll be like, oh yeah, 336. That always comes up. Okay, 5 people are chosen at a time, and 2 particular people must be chosen first and last. So again, someone's come in and pulled rank and said one particular person must be first, and I'm also going to force you to put one particular person last. You've got no choice there. It has to happen. So what happens in between here? Well, notice I've taken care of the restrictions first, which means that I've chosen 2 people of the 9 to go into those slots, which means I've got 7, 6, and 5 left for those spots. That's 7 6s, let's do 37 times. So 7 times 6 times 5. 6 5s are 30, 7 30, 7 3s are 21. That's going to be 210. All right, so there's your homework there, exercise 10B. All right, so we'll finish the lesson by going through some of the things on selections. So think back to the example about the runners. At the end of the carnival, 3 of the group of athletes, Jackie, Lucy, Sarah, Alex, and Mary, were chosen to clean up. List the possible groups for cleanup. All right, now let's go back and think about that. Okay, so we've got the same situation here, Jackie, Lucy, Sarah, Alex, and Mary. And what I want to do is work out who cleans up. All right, so this is a possible arrangement. This is a possible arrangement. But notice here that this is a race, or these were done as a result of a race, which means order matters. If I'm choosing people to clean up rubbish, no one cares whether you're chosen first, second, third, etc., etc. You'd be like, oh, got chosen. Doesn't matter, oh, he chose me first. Oh, I got chosen second. I got chosen third. You wouldn't care about that. So actually, in this situation, order doesn't matter. So this selection here is exactly the same as this selection here. All right, JLS or JSL is no different if we're picking up rubbish. You're just picking up rubbish, picking up rubbish, picking up rubbish. So actually we can get rid of that. We can get rid of that. We can get rid of that. That. They're all the same selection. All right, which leaves us only with those ones there, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is important to note that with the next exercise that we're going to do, selections, the total number of groups possible in this case for cleanup is equal to 10. Okay, the total number of arrangements for finishing the race is equal to 60. So compare this to the number of ways the first 3 places in the race could be filled. That was 60. Are they the same or different? Why? Because in this one here, in picking up rubbish, order does not matter. Okay, so like if your mate was sort of saying to you or bragging to you, hey, yeah, Mr. Miller picked me. Do you notice that Mr. Miller picked me first to pick up rubbish? You'd be like, well, doesn't matter who got picked. We just got picked for grabbing rubbish. All right, so places, arrangements, and permutations. So recall the formula here. We had, what was it? We got 5, and we're choosing, what was it? 3 of them. This is the racing option, arrangements and permutations for places. Now that was going to be 5 factorial over 5 take 3 factorial, which is 2 factorial, which is 5 times 3 times 2 factorial over 2 factorial. I forgot 4 in there. And remember that they cancel out. 5 times 4 is 20, and that's 60. Now notice that if we're looking at groups of 3 and we're doing combinations rather than permutations, okay, this is now talking about the context of rubbish cleanup, then those 60, what I do is I divide it by 6, okay? Now why 6? Well, you notice that back here on this page here, there was, or each particular one, this variation here, SAM, could be rewritten 6 different ways. But the 6 different ways don't matter. So what I do is to vet those options out, I simply divide these 6 by 6, leaving me with one particular arrangement, okay, or one particular selection rather. I've got to be careful with my language here. So SAM is the same selection as SMA. It's not the same arrangement, it's the same selection. Okay. All right, so going back to this then, what I can do, where was I? Okay, is divide the number of different permutations or arrangements by 6 to get the selections. And notice that that 6 can be written as 3 times 2 times 1. And with a bit of fancy number manipulation, what we can do is do 60 over 6 is the same as 5 times 3 times 4 times 2 factorial over 3 times 2 times 1 times 2 factorial. Rewrite it like that to get the 10. Now, why would I do some of this fancy footwork if logic tells me that that's what I have to do? Well, it's handy because that's the formula. All right, so if I'm doing it via the formula, come back. If I'm doing it via the formula here, I've got, when we choose R objects from a total of N objects in which the order does not matter, we can use combinations. So NCR or N choose R objects can also be written syntactically like that. And this is the formula, N factorial over N take R, which you'll notice is the permutations formula with this added to it. And that part of it just narrows down options or gets rid of the repeating. Okay. All right. And look, if you want to sort of be a little bit of the corridor language police, if you hear anyone talk about their combination lock, you've got to correct them on this, that actually it should be called a permutation lock. Now, why? Well, a combination lock is a situation where the order does not matter. So if your combination is 26, 13, 6 for argument's sake, if it's actually a combination lock, then 26, 13, 6 is the same selection or combination as 6, 13, 26, okay, because that's a selection, okay, or a combination. Now, really it should be called a permutation lock because order matters. You can't have a combination of 26, 13 and 6 and go, well, I'd prefer to enter 6, 13, 26. That is it, okay? So that combination or that arrangement is different from this arrangement here, and therefore we can't use the word combination. You see, I was about to use it then, okay, because I'm so used to calling it a combination lock, but it should be called a permutation lock. All right, so let's get stuck into a little bit of this. We're not going to get too much further into it in the class. If order doesn't matter, how many ways can you select 3 people from 5? We write that as 5, choose 3. So how many different ways can I choose 3 people from 5 people? That can be written semantically as 5, 3 like this, which if we use the formula is N factorial, that's 5, N take R, 5 take 3 is 2 factorial, R factorial, which is 3 factorial. We can simply just go to town on the factorials to work out the 10 there. 98 students from 100, choose 98. You might think that that's really difficult, but remember we've got 100 times 99 times 98 factorial over 2 times 98 factorial. They cancel out, 1, 50, and that's going to be 50 times 99. That's going to be 990 times 5, and that is 4950. Oops, 4950. All right, so looking at some more stuff here. Evaluate these without a calculator. 7 factorial over 4 factorial times 3 factorial. So using the formula, so I've got 7 choose 3, that's the formula's produced that. Let's go ahead and simplify. 1, 2, 1, 3, 1. So that's going to be 7 times 5, which equals 35. Okay, now you can do this on the calculator as well. So here's NCR, and you choose 7, 3, which is 35. Okay, 7 choose 4. 4s cancel out. 1, 1, 35. All right, 6, 2, gone. 15. Gone. All right, so that's going to be 10 times 9 times 8 factorial over 2 factorial times 8 factorial. They'll cancel out. That's 2 times 1, so that's once, 5, 45. Can you guess what this one is? It's going to be 45 as well. What did you notice? That on either side, so if I've got 7 choose 3 and 7 choose 4, on either side of this, I'm going to get the same amounts. Okay, now that'll be an interesting property that we explore a bit later on. Okay, how many different ways from 4 objects can I choose 1? Well, think about it. If I've got 4 objects and I choose 1, I can grab this one, or this one, or this one, or this one. That's going to be 4. How many can I choose? 3. Well, interestingly, whoops, that's going to be 4 as well. I can grab those, I can grab those, I can grab that and those. There's 3, and the 4th is somewhere there. All right, 6 choose 1. Well, that's going to be 6. Can you guess what 6 choose 5 is? That's also going to be 6. 8 choose 1 is going to be 8. 8 choose 7 is also going to be 8. Right, here's an interesting one here. 5 choose 5. So we've got 5 things there. All right, how many ways can I do it? Can I choose all of them? Well, the answer is 1. How many could I choose? How many different ways could I choose none of them? Okay, well, I would say I'm not grabbing any of you. That's the way I'm going to do it. There's one way I'm going to do it. None of you. All right. So important to note that 5 choose 0 is equal to 1. 6 choose 6 is 1. 6 choose 0 is 1. 8 choose 8 is 1. 8 choose 0 is also 1. All right, and that's where we're going to stop. Okay, and we'll finish off combinations in the next lesson.